All right, welcome back, everybody. Yesterday, we looked at the relationship between force and acceleration, and what we wound up seeing is that when we compared data values, we determined that for a mass of m, the slope of our line that we're looking at is going to be 1 over the mass, which led us down to work out this idea. We already knew that acceleration and force were directly related. There was a linear relationship. We could see it on the graphs. We found this, and we wind up here at F equals ma. Now, as we go through this, this is a very, very, very important idea that we are going to re-summarize here in just a moment. But I want to think about the units with these. So in our notes, if you write it exactly like I do, which I imagine a lot of you do, I'm going to have a little spot here and say, let's think units. Now, for these, we already know, and maybe we don't, we're going to see if you remember, when we talk about force, we don't use pounds or kilograms, we use what unit? We've said it, but we've never really talked about what it is. A Newton with a capital N. So, right now we have force, and then I'm just going to, underneath, we're going to play the unit game. In newtons is exactly equal, and I'll do parentheses here, to mass times acceleration. That's the end result of what we saw yesterday. In which unit do we measure mass? Kilograms. And which unit do we use for acceleration? Good, meters per second squared. And if we just multiply it straight through, we wind up seeing that 1 Newton is exactly equal to 1, and this is an ugly unit for a minute. It's kilograms times meters per second squared, right? Which is ugly. Kilogram meters per second squared. Now, it turns out that this is the way that we measure force. It's kilogram meters per second squared. And it sounds wonky. It's called a Newton. That's it. Now, when we talk about this, the unit does make sense, but you can't get a good feel for it just right here. Can you imagine you have a 1 kilogram block sitting in front of you? And I can go grab 1 kilogram if you want to get a feel for it. I have Newton scales right here that we're going to play with in just a minute. A kilogram's small, 2.2 pounds roughly. Okay, if you have a single kilogram, is there some amount of force that without friction you could get 1 kilogram to accelerate at 1 meter per second squared? Does that force exist, do you think? To accelerate a 1 kilogram mass at 1 meter per second squared. So after 1 second, it's going 1 meter per second. After 2 seconds, it's going 2, and 3, it's going 3 meters per second, and so forth. That force exists, right? That force is 1 Newton. That's what it takes. Okay, 1 Newton here is a nicer way to write it than this, but the unit game will wind up happening. Now, for our own kind of idea, if I asked you to apply 1 Newton of force, any idea? Probably not. So I'm going to give you like 2 or 3 minutes, random stuff around the room that you will have access to again. I'm going to give each of you a scale here, and I'm going to have to show one up on the screen. So will you share that with Ricky? You share that with your table. You guys share it. And I'll give you guys one to share here in just a second, okay? All right. So I think my camera will work. We'll find out. Hey. All right. So here is my Newton scale, and it's not backward, which I didn't even realize I was flipped. Now, as I look at this, we need to make sure it's calibrated. These ones, if you have one like this, all I'm going to do, there's a little tab up on top. I'm going to pull that or push it until it's calibrated. So I push down, and all of a sudden, I see that it's right at 0. Okay, those ones, I believe it's the top. They should already be calibrated. Okay, so these spring scales do 2 things. They give you grams, and they give you newtons on the other side. I'm going to pause this, and I want you guys to weigh various things around you. I'll go get us a couple kilograms and half kilograms and stuff like that just to verify, but I want to give you guys a second to do this. So we got a few common objects. Okay, has everybody had a chance to feel either the half kilogram or the full kilogram? Is a kilogram more or less than you thought it would be? More? Okay. Like that one's really dense in newtons. So, what are some random things you guys just weighed? This is really loud today. Okay, so you have a clamp. How much did that clamp weigh? Clamp was 1 Newton? Okay. I wouldn't write down all these if you don't know what they're talking about. What else? You guys weighed that water bottle, right? Is it full? And how much did it weigh? 5 Newtons? More than 5 or more than 10? So half full water bottle was more than 10. Okay. Now, if you want to try to calibrate this with 2, I mean, you can find it if you have 2 of them hooked up. They'll just split the force and you'll just have to combine them. So that's like a hydro flask bottle. So we'll just go ahead and here. And I oop. So a hydro flask half full, when you use 2 of those, is it still enough or is that? What do they come out to? 2 and 3? Well, something wonky's happening there with springs. You're what? 9 Newtons? Do you have a hydro flask or don't you erase it? Okay. So I'm just going to say bottle. Is yours full? Okay. So it depends on the bottle, right? That's a weird thing. What about a 1 kilogram mass? 10 newtons. About. There's a little bit of rounding there. What about the half kilogram? 5 newtons. Okay. You could weigh like whatever you wanted, right? We could get bigger, fancier scales. Possibly. All that you're good? Yeah. Okay. All right. Now, as we go through here, there's a bunch of ranging things. Your book uses silly examples. A nickel is like half a newton, or sorry, 20th of a newton, so 0.05 newtons. A nickel is super light. Yeah. Okay. Beyond that, people. Depending on the person, obviously, but I have that a person like 70 kilograms, which is pretty close probably to what I am, 680 newtons. So most people in here are probably between 600 and 750-ish, depending on the time of day and whatnot. Cool. Now, remember that this is a force, so when we look at it, it's the force that gravity is pulling on us. Beyond that, cars have to use force to accelerate, right? And I hate that your book does this because they don't specify the type of car or what the context is, but they say that a car accelerating is like 3,000 newtons. Like, no idea how fast it's going. Then you give another silly one like a spaceship. It's like 300 million newtons or something. It's ridiculous. Okay. It will pretty much all be in newtons moving forward, just so you guys are aware. Now, yesterday I asked if this looks familiar to anybody, and I don't remember what you guys said. Do you ever remember seeing F equals ma? Do you remember where you saw it? It was probably with my wife, I would guess, if you had Mrs. Holloway. Anybody remember what this is called? All right. So that's all right. There is a pretty important guy in the history of physics that we have talked about before and we'll talk about again. I'm going to approach this a little bit differently than I did it in my notes, but that's okay. When you think about the man, the myth, the legend that discovered all this stuff for the first time in Western civilization, we're in England in like the 1600s. Who are we talking about? Please don't break my stuff. I'm just teasing you. Who? So Galileo was fantastic, right? Galileo is the guy that discovered that objects accelerate at squared. That was his big contribution. He did a lot more than that, just so you know. But Isaac Newton is also a large name, right? And Isaac Newton made some observations about what happens in nature, not why things happen. There's a difference in those two ideas. If you have an explanation of what occurs in nature without any explanation of why, that's called a scientific what? So the theory is the why. We refer to the what as a law. Turns out Newton discovered several of these. We are going to look at Newton's laws. Okay. Here they are. As we go through, we're going to look at 2 of them today, and we will see the third I think, in next lesson. But here we go. Newton's first law, and I'm going to make this all caps. Newton's first law. This is going to get real old real fast if we write them all out like this every time. Anybody opposed to N1L? N1, we can do first rather. N first L. This is not accepted shorthand. This is my proposed. You don't like it? Was there another one you want to suggest? NFL is pretty common. Yeah. NFL? Yeah. Okay. That's exactly where my head went too. Waiting all day for Sunday night. All right. Newton's first law. I don't really care which one you write as long as you're consistent. NFL, NSL, and NTL for the third. Okay. So as we're looking at this, Newton's first law, we have not discussed yet, but you guys will know it. An object at constant velocity, and then I'm going to add so we don't have to write like a ridiculously long thing, and I don't even think I have to add it. Is 0 a number? Could your velocity be 0 and stay 0? So notice I'm saying an object at constant velocity, which implies two things. It could be moving, or it could not be moving. Everybody cool with that? Because normally when you see this, it's an object at rest or in motion is how we word it, but this is a more precise. An object at constant velocity stays at constant velocity. Unless something happens. What has to happen to change an object's motion or its velocity, which, gosh, that has another name. A change in velocity, what's that called? Acceleration. And to create a change in acceleration, you have to apply something to it. A force. An object at constant velocity stays at constant velocity unless acted on by an unbalanced force. Okay, that is Newton's first law. What this comes down to and what you may see this as, and depends on, I don't remember how it gets taught in middle school, but from time to time, you may see Newton's first law referred to a little bit differently as the law of inertia. I'm going to sneak a vocab in here. The law of inertia is pretty regularly another way to think about Newton's first law. You guys ever heard the word inertia? Do you remember what inertia is? Okay, that's fine. Inertia, and this is going to look wonky just because I'm going to sneak it in here. The tendency to resist a change in motion. So if something has a lot of inertia, it's hard to change its motion, which this is obviously true. If I asked you to push your desk over, could you? I think so. If I said, okay, go push over a car, could you? Probably not as easily because the car has much more inertia, probably due to its what? Its mass. That would make sense. Okay, the law of inertia. Now, all of a sudden, this first law brings in a couple additional little topics. One of the big things that we're going to see over and over and over and over is this idea of equilibrium. And one more definition here. And I'll use a serif. Equilibrium. Now, this is a big, fancy word, but luckily, you've all seen words before, and I think we can probably reason this out. If something's in equilibrium, what do you think we're going to say about the forces? They're equal. That makes sense. Now, what that means in its entirety is the net force. And I'm getting confused between this class and my other class. Have we used the language net force yet? Okay. F net, remember? Yep, because we use the subscripts. Okay. The net force is equal to what? If it's in equilibrium, which means everything's balanced. If I'm pushing with 5 newtons this way and 5 newtons this way, what do they do to each other? They zero out. So the net force on an object would be 0 newtons. That's all it means. Now, when we look at these, in reality, it's super duper hard to have more than just these two forces, right? Because there's gravity, there's friction, there's air resistance in the real world. But in here, we get the nice physics for now. Okay, Newton's first law. Does this sound familiar? An object at rest stays at rest, and an object in motion stays in motion. All right, the last thing, and man, this is a big section. Okay, beyond that, we get Newton's second law. Newton's, and this one, I don't know that any of them are really more important than the others, but this is the one that I consider the most important, and it's the one that we're going to use most frequently. And we'll use NSL for that. Okay, Newton's second law. There's a wordy version of it that I think we can avoid. Okay, Newton's second law, we've actually discovered this one yesterday as we were playing around with stuff. What it says word for word, the acceleration of an object is directly proportional to the net force and inversely proportional to the mass. All that this works out as, and this is the part that I care about, is that it reads as a different version of this, but it all boils down to the force of an object, or the force it's exerted, is exactly equal to the mass times what? Acceleration. This is Newton's second law. Now, if we rearrange this, do you guys agree it could be this? F over m? Now, that's what, when we look, if you look in the book and you look at the ugly wording that it has, this is what it's saying, that, hey, it's directly proportional, acceleration is directly proportional to force, A equals kf, and then it's inversely proportional to the mass. That's all exactly what we saw yesterday. This is the more common way, but we can rearrange it as needed. All right, we got two problems to do, and then I'm going to cut you guys loose, and we should have some time for homework today. Questions about Newton's first or second law before we do just examples? All right, so now I have to decide where do we do examples on. Because we'll do it here. All right. So just a heads up, if you guys look at the videos or the notes online, I don't know that these examples are going to be there. I think I zoomed in too much. Or too little. There we go. All right, so a couple examples. Start with a hard one or an easy one? Do the hard one so the easy one seems easier? Okay, here we go. Examples. Now, what I like about presenting stuff out of order than the way that I did it is now it means that we could use either law as we're looking at it. So here we go. Oh, this is a cool problem. I actually think we're just going to do one problem, but it's going to have several parts. So here we go. We have... Oh, that's not a hard problem. Lame. That's okay. We have two horizontal forces. Are exerted on a large box. And I don't really care there's a large box. I'm just going to get on a box. Okay. Two forces acting on a box. That's where we're at right now. The first of these two forces is, let's say, 373 newtons to the right. And the second is 173 newtons to the left. Okay, there's what we have. Step one, or part A of this problem. I want you and I'm going to give you guys to do it first. I want you to draw me the free body diagram, which remember that's FBD. I want you to draw the free body diagram. On part B, and I think we can do both of these without my help, but I'll come around to help just in case. I want you to find the net force acting on this box. And then as you guys are working on A and B, I'm going to move down just a little tiny bit for example C, and I'm going to type it because that's a new thing that I learned to do and I don't implement very often. Okay, talk with your neighbors. Free body diagram. You can draw a picture if you want. Doesn't have to be a picture. Free body diagram and net force. I'll give you a couple minutes. As we're drawing this, remember that we need to make sure that we have a dot for our object, and then all the forces originate from it. I don't care if it's being pushed or pulled. The end result's the same. It's going one direction or the other. Okay, my first force, 373 newtons to the right. My second force, 173 newtons to the left. I don't need to measure it, but I need to be kind of to scale. If I said that's 373, would you believe it if I said this one is, like, it's obviously smaller? I'm going to label this as force 2, just to keep track of stuff. And this force is 173 newtons. What do I need to add, though, to verify or to make sure that it's clear that it's different than the first? Negative. It's the opposite direction. Could I have chosen this to be positive at 173 and negative the other way? I get to pick, right? It's entirely up to us. I would rather not, but you could. Okay, to find the net force, it's literally just the sum of all the forces acting on the object. How many forces have we identified acting on this object? Can we add them up? Yeah, let's do it. The net force, super easy to calculate. I'm going to write out much more than you might, but do you agree the only two forces are force 1 and force 2, so we just add those up? Baller. That's 373 newtons plus a negative 173, and we wind up with how many newtons? 200 newtons. Is that a lot of force? It's a weird question to ask, right? Less force than I pushed down on the ground standing here, because I would say I'm about 700. So I'm pretty close to 200 pounds. So 700, that's like what? I'm just going to say I've gained weight and I'm 800, so this is an easier calculation. If I were 800 newtons, that's a quarter of my weight. We're looking at like 50 pounds, which not a ton. Everybody in here can exert 50 pounds of force, I guarantee it. Okay, not a crazy amount of force, but there it is. That's our net force. Now notice the sign on it. Positive or negative? Which means if this box moves, which it will in part C, when this box moves, what direction should it move? To the right. The acceleration is always in the direction of the force. Okay, so here we go. We now get this problem. We have it initially at rest, and these people or whatever it is acting on it start pushing with these forces, and the force going to the right wins. We know its speed after 5 seconds. I want us to find the mass of the box. And let's go ahead and start with our knowns. All right. I'm stuck. Help. What do I know? Ooh, time. 5 seconds. Good. And once again, I'm stuck. I need help. Mickey, we made eye contact. I know my initial position. Don't know that we need it, but I love it. 0 meters. Good starting point. Rafa, you had your hand up. What else do we know? I know my initial velocity. I don't ever tell you the initial velocity. Oh, but it's at rest. What is my initial velocity? Bet. Sorry, wager, if you will. After 5 seconds, I would call that its final velocity. Nope, VF. Sorry. 6.5? Anything else I know? There's one more thing. Sneaky. We've already done work. Ooh, the net force acting on this object. What's the net force acting here? 200 newtons. Okay. What are we trying to find? I'm trying to find the mass of the object, and right now that is reasonable. That's maybe all that we need. Let's try to think this out, though. I want to find acceleration. I know that there's a force. Do any of these equations have force in them? Well, shoot. Is there an equation that relates force and mass and any of these other things we know? So, say that again. So, love it, but we did a bunch of work to figure out what K was. It's really A is equal to F over M. Okay, I'm going to rearrange that all the time. There's only one equation, and it can rearrange as many times as you want. But there's only one equation that we've seen that relates force and mass and acceleration, and it's this. Force is equal to mass times acceleration. All right. As we look at this, there might be some issues. I can solve for M, no problem. What would you divide both sides by? A. I'm cool with that. Mass M is equal to force over acceleration. All right. What's the force? 200. What's the acceleration? All right. Well, the good news is that we can find it. Maybe we need that one too. We just don't have it yet, but I think we have enough to get it. So we know the force. We need the acceleration. What's acceleration? I'm going to take a little side trip here, and then we'll come back to it. And there's a lot of answers to this, but based on the information that we have, I think I can find it. Change in velocity over time. Or, if we want to write it all the way out, VF minus VI over TF minus TI, but 90% of the time, at least at this point, we just use 0 for TI, so I'm just going to call it time. How much of my what was my final velocity? It was 6.5. Okay, so we'll go ahead and say that's 6.5 minus, what was my initial? 0 over 5. All right. You have a calculator open already, one of you two. Will you give me this number? 1.3? Like exactly 1.3? Or 1.3? Weird. Is it 1.3 repeating? Weird. I can't mental math apparently. Okay, 1.3 watts. Meters per second squared. And if you need justification, meters per second. There it is. Okay, now that I know this, can we use this? Do it to it. Use the force that you have and the acceleration that we just found and determine what the mass of this object must have been. 200 newtons over 1.3 meters per second squared. And this gets to be a weird idea. So you're all going to get the number inevitably. I want to see you showing the work that leads to the fact that you wind up in kilograms rather than just saying, oh, I know it's kilograms because it's a mass. Show me the unit gain. Sorry? So let's see. So close. How do we measure newtons? So careful. And so we're going to see here. Where's that? This one? Okay. So let's check it. It's newtons over meters per second squared, right? What's a newton? It's on your page, and I would use that unit. What's the number we get just for the number? Okay, so I'm just going to say approximately 154. Now, I'm claiming that I know this is kilograms, but I'm asking that you guys do the work to verify that. Goes okay, goes poorly. All right, prove it. What's a newton? And I'm going to play the unit game here. Newtons over meters per second squared is what I'm thinking about now. And I've written the fraction as real fraction now. This becomes something. What's a newton? Kilogram meter per second squared, and I'm dividing by meters per second squared, which is like taking this and multiplying it by what? Second squared over meters. Dagon. What are we left with? Hey, is that how we should wind up if we're talking mass? We done. Okay. I think that we just got number 6 up here. We should probably include F equals MA, I would guess. I'm going to change colors today. I'm actually just going to go to poster board. I wish Riley were here. I was going to make her write it. Anybody else have really pretty font? I'll come look at your page here in a minute. I might have a project for you. Cool. Seem doable? Good. I want you guys, you get 15 minutes to start right now. I'll just add it to the Google Classroom. Sure, let's reload that. Don't log me out. Don't log me out. Okie dokie. So today we have October 9th. And your homework, starting right now, is homework 4.1. You will find this. And this is weird. I would just call it page 99. But just so you know, it's on two different pages. It's 97 and 99. Did we talk, if I didn't tell you the page number, how would you possibly find it? If you just go to section 4.1, you would find the numbers that I'm about to give you. If you want to include both those, you can. You get the problems 9 through 15. But I want you to skip 11 because I'm pretty sure we did it. Cool. And I just did that way wrong. But that is your homework. We'll do it right there. And this is finishing 4.1. Newton's first and second. All right. So your homework will be due tomorrow, just so you guys know. Due 10:10. Cool. 13 minutes at this point to start and knock that out. I'll have you do that right now. Yes.